All right, let's do extended response items. So, hey, I have a brother named Greg. Greg started with a certain number of quarters. Then he decided on a number of quarters he would save each day. He added the quarters he saved to the amount with which he started. At the end of day 2, Greg had a total of 26 quarters. So I'm just going to write this down really quickly. So at day 2, I had 26 quarters. At the end of day 5, he had a total of 35 quarters, which meant I saved 9 quarters in 3 days, which means for my slope, 9 over 3 is 3. So that means I'm saving 3 quarters every day. All right. It does say show your work or explain your work. And so I'd probably just do this. So we have a rise and a run, we have our slope. All right. And so then you do have to state the answer. 3 quarters per day. All right, write an equation to model the number of quarters Greg has saved. Y after x days. So we know we're going to do y equals mx plus b. We already know our m value is equal to 3x, but we don't know how many he has saved, or how many he had to begin with. So really, if we're saving 3 quarters every day, I could work backwards in my table, probably the easiest way to do it. So at day 1, I would have 26 minus 2, sorry, 26 minus 3, so it's 23. And at day 0, which is where you would start, we would have 20. So that means my y-intercept is equal to 20. So my final equation is y equals 3x plus 20. Now I could also have taken a point, oh no, let's take this one, and plugged it in. So in using that method, my y value would be 26 is equal to 3 times my x value, which is 2, plus b. 3 times 2 is 6, plus b is equal to 26. Now clearly at this point b has to be 20, because 6 plus 20 is 26. Using the rate at which Greg is saving, explain why he can never have exactly 100 quarters at the end of any given day. So let's do this. So we have 100, which is our y value, because that's how many quarters is saved, is equal to 3x plus 20. And let's go ahead and solve it. Minus 20, minus 20. So we get 80 is equal to 3x divided by 3 divided by 3. And clearly 3 does not go into 80. Evenly, I should say. So you'd end up with x is equal to 2, carry the 2. 3 goes into 26 times. So this means that he would have 100 quarters after he found his first quarter on the 26th day. But that's not the end of the day, because he'd go on to find 2 more. So it would be easiest to say that at day 26, he has, 99 quarters. And at day 27, he has 102. 100 quarters would occur in the middle of day 26. And you definitely need to show this work too. This is just as good of a mathematical explanation as an English one. All right, D. Starting with day 2 and going through day 20, Greg created a graph to show the relationship between the day and the total number of quarters he had saved at the end of that day. Greg plotted each of the 19 data points and then connected them to describe what it looked like. Well, we know we have a y equals mx plus b relationship. You know this is a linear relationship. And a linear relationship would look like a line. So you'd have to say it is a line with a slope of 3 and a y-intercept of 20. Right, that problem's easy enough. Alright, the standard length of a basketball game. Alright, and question 1 asks us to make a line of best fit. So I'm going to use my line tool. You would have to be using a ruler. And this is not a perfectly linear relationship, but it's fairly close. The number of years you play in the league, the more minutes you play per game. And so my line is going to happen somewhere in there. So I would say it looks maybe something like this. Now, I would have, notice how I have a lot of points above, I have a good number below, and we have this one outlier, the kid who's played 3 years and is only getting 6 minutes of playing time. We all know that kid. It's really cool that it's still playing, quite frankly. What is one way the line best fit would change if you remove the data point that represents that one kid? Well, without this outlier, I would conjecture that the line would probably slide up. So I would probably say that the y-intercept would change. Also, it is conceivable that you would have potentially a slope that would be a little bit steeper, maybe something more like this. But as it stands, we do have that child. And so let's go back to what we had before. There we go. Forgive me if I don't write it down. Based on the line of best fit that I drew, what is the average number of minutes per game a player who has never played in the league before would expect to play? I'd say about 15 minutes. Because that's the y-intercept. Explain why the line of best fit would not provide a valid approximation for a kid who for the average number of minutes a player who's been playing in the league for 15 years to play. A couple things. Most leagues wouldn't have 15 different divisions unless they started at 0, which would be ridiculous. Well, I guess it's possible if you start at 4 and played through 19, but at 19, most kids are not playing league play. If they're still playing, they're playing through their college. So, if this line were to continue, we would end up with a number of minutes per game that would exceed the number of minutes there are in the game. And actually, we've already done that because it isn't until the NBA that you go over 40 minutes per game. So this dot is a little ridiculous because it defies reality. So that's why it wouldn't make sense to continue, because you can't have that many minutes. Alright, that's all 4 of them. Moving on to the next problem. Oh yeah, linear equation.